So it's an honor to me to present Professor Rafael Murrieta Cid. Like the rest of our speakers, he also has a very good and impressive CV. So Professor Murrieta received the BSc degree in Physics Engineering from Monterrey Institute of Technology and Higher Education, Monterrey in Mexico. That happened in 1990, and he got a PhD degree from the Institute National Polytechnic in Toulouse, France in 1998. His PhD research was done with the Robotics and Artificial Intelligence Group of the LAAS CNRS in 1998-1999. He was a postdoctoral researcher with the Department of Computer Science in Stanford University in the United States during 2002 and 2004. He was a postdoctoral research associate with the Beckman Institute and the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign in the United States. From 2004 to January of 2006, he was a professor and director of the Mechatronics Research Center in Tecnológico de Monterrey, CEM. Since 2006, he has been with the Centro de Investigaciones en Matemáticas in Guanajuato, Mexico. In 2016, he was on a sabbatical leave at the University of Illinois at Urbana-Champaign. His research interests include robotics, motion planning, and control theory. So please join me and give him a big applause to Professor Murrieta. Thank you, Rafael, please.
First of all, I want to thank Jose for the kind invitation. It's a great pleasure for me to be here. It's an opportunity to meet colleagues and students, and it's a great time for me to have the opportunity to talk about this work that is mainly done by my students, of course, but it's me that is going to present, or try to present this work today. And the name is Pursuit-Evasion Problems with Robots. Thank you. Pursuit-Evasion Problems with Robots, which in Spanish the translation is more or less persecución, evasión. There is two agents, and pursuer and evader, un perseguidor y un evasor. And the guys are has opposite goals. For instance, one wants to capture the other, while the other wants to avoid capture. Okay? So it's a no cooperative game. And I'm going to talk about two versions, well, actually three versions of these non-cooperative games. I am going to, well, I think my goals today are two. One, try to explain what are the problems in general, I mean, only the problems, and try to give you some ideas about what are the tools, the techniques that we are going to use, or that we have been used to address those problems. Of course, I will not present this in detail, but if I can get these two goals done, I will be happy. Which are the problems? Which are the main techniques that we have been using? Okay? So, the outline of my talk is this, the introduction. First of all, I'm going to talk about a pursuit and evasion game in an environment without obstacles, where you have two agents that are heterogeneous. The pursuer is faster than the evader, but the evader is more agile, can more easily change the motion direction. And then I'm going to talk about another related game in the presence of obstacles in this space. The first one is about open space, okay? And finally, I'm going to present the conclusion and the future work. And this is one version, the first version of this problem. And it's called target capturing in an environment with an obstacle. You can think this is the robot. There is actually a robot with wheels. and this is the evader. That can be, for instance, a human being, okay? And the goal is to get the pursuer closer than the evader at a given distance, what is represented by this circle, okay? So what I want to do is that this guy gets closer to this guy at a given distance to get the system to this condition, okay? And typically, in this kind of games, the pursuer is faster, it can move to a bigger speed, but it cannot change the motion direction instantaneously. It's like a car, okay? A car has some wheels, and the cars cannot move in a perpendicular direction to the wheels. And the evader is slower, but is more agile, okay? And one guy, the evader, wants to avoid capture, while the other guy wants to capture the evader. This is the first game, and I think probably this is the most well-known work about that. It's called Differential Games, and the author is Isaacs, where is I would say a mathematician that was working with Richard Bellman in the 60s and worked in this kind of problem. And you can find literature about these problems in journals such as the Transaction of Automatic Control. The second problem is related, but is not exactly the same. In the previous one, there was not obstacle. There was the free space, okay? Here, you have some obstacles, and you have, again, two agents, the pursuer and the evader, and the goal is to keep the evader inside the field of view of the pursuer. It's, you know, like a paparazzi that has a camera and wants to get the other guy, all the time inside the field of view, okay? And this guy, what wants to do is to get outside the field of view of the other by using the obstacles to hide behind an obstacle, okay? And you can assume that both guys have the map of the environment, or you can also assume that the guys are discovering the environment as they move and reason about local maps of the environment. So this is the second version, what is normally called target tracking, okay? And it's about maintaining visibility, yes? One guy wants to see the other, and the other guy wants to escape the surveillance of the other guy. And finally, this one, that is the one that I go not to describe in more detail in this talk, this one is about target finding in an environment with obstacles. So the goal here is like, let me put this in a simple way. It's like to play hide and seek, okay? One guy, at the beginning, there is no visibility between the agents. There is, again, a pursuer and an evader, and the pursuer wants to find the evader in the environment. What means by finding, I mean to establish a line on sight between the guys. And the other wants to remain hidden in the obstacle. So, in some cases, for some environments, it is possible to guarantee that the pursuer is going to find the evader regardless of how fast is the evader. For instance, here, possible, you know, what is in blue is the pursuer, the blue circle is the pursuer, the yellow region is the region that is seen the pursuer at this time. The green part of the map is, the gray part of the map is that had not been seen yet by the pursuer, and the white part is that had been already seen by the pursuer, but is not perceived at that moment, okay? So the goal is to get all the environment cleaned, I mean to make everything white, while there is not something that is called recontamination. Recontamination is the possibility for the evader to sneak in a part that had been already explored without being seen, okay? So this is the third problem. And for instance, there is a very famous paper about that problem. Actually, I get involved in this kind of research with those guys, and they were reasoning about in which environment can I compute a path such that I will find the evader regardless of how fast it can move, okay? So for instance, in this environment, in this one, the pursuer can travel this path, and it will eventually find the evader because it can know. For instance, when the pursuer is here, if the evader tries to snake here, they will see the other passing. But in this kind of environment, there is no path. It's not possible to find the evader without considering how fast is the other guy. Because when the pursuer is going here to see what is in this portion of the environment, the evader can move very fast and hide here. Okay? So basically, that is, I have to accomplish my first goal. Those are the problems, right? There is three versions. One is to capture the other, to get closer than a given distance. The other is try to maintain the other in view. And the third one is one of the guys want to find the other. And of course, there is some, I will say, nice application for that. For instance, automatic cars in supermarkets, on airports that can follow you, carrying your luggage or some stuff that you want to get with you without carrying this. For instance, this thing. Or surveillance and monitoring of childs. For instance, you can get a robot that is always maintaining visibility of the child while you are, I don't know, in your office and your child is in your house. That will be really nice and will be, you know, not about war, no problems. It's just, I want to surveil a child. And another one, it may be, you know, convoys of cars. Well, one car is following the other one, and just the first car is driving by human beings, and the other ones are automatically following the first cars. And actually, that will be very good to reduce traffic jams, because there will be coordination. So there is some possible application, and actually I had not been worked before in drones, but when Jose invited me, we thought, both of us, that the theory that we will describe later, it may be used in the case of drones. I think that will be very, very nice to have a game where you have drones that are chasing one to the other, or are maintaining some formation. So this is the kind of application for future work that we have in mind. So now, I will try to describe very intuitively which are the mathematical tools that we are using to model these problems and to find a solution. And I also want to try to describe which are our main results. Oh, before that, this is an experiment that I did long time ago, like 15 years ago in Stanford, where we have a system that was working with two robots. This was the evader, this was the pursuer. this guy is trying to maintain visibility of the other guy, while the other guy is trying to hide behind an obstacle. And there was a system. There was a lot of teeth runnings on the robots. This guy has a visual target tracking, and is tracking those barcodes. We simplify the vision problem with us. It was a good idea because vision is hard. So we use these barcodes, and there is another camera that has pointed to the ceiling to see landmarks, artificial landmarks in the ceiling, localize the robot, and avoid collision between these guys and the obstacle. And this is the kind of results that we got at that time, 15 years ago. Ooh. Oh. I think I'm okay, Luis, thank you. Here is the video. I will be playing it again. This is the pursuer trying to hide behind an obstacle, and the evader is like preventing that the other guy is going to hide behind the obstacle. Okay? Of course, the robot was moving slowly. It will be good to have a much more dynamical system, and we use artificial markets. There is a lot, I think, a lot of work to still be done in this kind of things. And some other possible application, what I think will be cool are those ones. Multiple evaders and multiple pursuers. Here you have the red guy, the red square that is following the red circle, and the white square, blue square that is following the blue circles. Those are the visibility regions, what is typically of the chains of the cone, like what is seen by the cameras. And now we will see that if it is convenient, the pursuers may change, exchange evaders. So this is cooperation about multiple agents. Another thing that will be nice to continue with drones, I think. And now, let's go to the math. The problem formulation is this thing. We have a differential drive robot and an omnidirectional evader move in a plane without obstacles. And you know, the gain is sober when the distance between the robot, well, first of all, what is a DDR robot, differential drive robot? It's a robot with two wheels that have two independent motors and can be controlled independently. So the guy can turn in place without translating to the difference of the car. And both players had maximum bounded speed, BP and BE, and the robot is faster than the evader, but the evader is more agile. And the problem is this one. The robot wants to minimize the capture time, and the evader wants to maximize it. So it's a min-max problem. We want to reduce the capture time, the other one to make the capture time as big as possible. And if the capture time is infinite, the evader wins. And if the capture time is finite, the pursuer wins. And in these kind of problems, there are two main gains. One is called the gain of degree, and the other is called the gain of kind. The gain of kind is answering the decision question, which player will win. Which player is the winner? And the second question is to say how the players should move, must move, in order to achieve their goals. So one is just a decision question, who is the winner? The other is how. How should the players move? One is called the game of degree, the other is called the game of time. And there is a known problem that is related to this one, and is called the homicidal chauffeur problem. What is, you had a car in a parking lot without bounds, and the car wants to run into a pedestrian, and the pedestrian wants to avoid that. And the solution for that problem was partially found in the 60s by Isaacs, the author of the book. But the difference with this problem and the one that I'm going to describe now, or that I try to describe now, is about the control profiles of the players. In the car-like robot, in the cars, you can push your accelerator to the limit and to turn the driving wheels to the limit at the same time. So you can get as fast to your maximal speed at turns to your maximal capabilities. This is the angular velocity, the linear velocity of the car. This is the angular velocity of the car. And this possibility is allowed. Yes? What is maximal translation speed, maximal radius of rotation. While in the DDR, that is not possible because of the motors that the DDR has in the wheels, it cannot rotate or translate at maximum speed. Either it translates to maximal speed in a straight line, or it rotates to maximal angular speed, you know, because of the independent motors. So that changed everything. The optimal controls for the two players changed because of this change in the mechanical system of the pursuer. This is the difference with the homicidal chauffeur problem. And a way to model the problem is like that. You have the Euclidean plane in a reference frame where if you use a global reference frame, you need 5 numbers to specify the configuration of the system. Those numbers are the position of the pursuer and the orientation of the pursuer. We need 3. And 2 numbers for the position of the evader. The evader is omnidirectional, so basically you don't need a number to describe the orientation. So in this global reference frame, you need 5 numbers, but there is a trick that is called the reduced space. In this space, everything is local relative to the pursuer. Here, imagine that you are an observer that are seen playing both players far away from those, for the players. And in this case, you are seated on the pursuer. And in this local reference frame, you only need 2 numbers to define the position of the evader with respect to the pursuer. And the reference frame, the y-axis of this reference frame is parallel to the wheels of the pursuer. So basically, you get a dimension reduction from 5 to 2, and that makes life easier. Because in 2 dimensions, you can visualize the solution, while in 5 dimensions, no way. You know, it's like a deterministic PCA We are reducing the dimension. And those are the differential equations that describe the motion of the evader in the reference frame of the pursuer. It's for this reason that the call is called differential gain, because everything is modeled with differential equations. Okay? And U are the controls of the pursuers, and B are the controls of the evader. U are the angular velocities of the wheel of the robot. And you have two angular velocities, the angular velocity of the right wheel, the angular velocity of the left wheel. While the controls of the evader are a vector. What is the velocity vector? The magnitude of this vector, what is called U1, and the angle of this vector, what is called V2. That is here. This is the vector. Those are the controls. So this is the basic at modeling. So which are the tools that we use to model this gain like a min-max gain? There is something that is called G, what is the payoff. It's the things that one guy wants to minimize and the other guy wants to maximize. And in the case of this gain, it's just time. Okay? It's the elapsed time, which depends on the controls and on the trajectories that follow the guys. But at the end, what matters is the time. And J, what is the payoff, under the optimal action of the guys, is called B, the value function of the gain. What is basically what we want to compute is what is unknown. And the value function of the gain is the payoff on the optimal actions of both guys. And what we want to get is the Nash equilibrium strategies for those guys. And a strategy or a policy, for me is a synonymous, is just a function. The input of the function is normally is the state, and the output of the function is the controls. There are open loop motion policies and closed loop motion policies. An open loop motion policy is something in which the input is time. So basically, what is governing everything is the time. If you say that there is a closed loop motion policy, so the input, it may be the state, the position in this reduced local reference frame, or even the observation, measures from the robot sensor. But basically, a motion policy is a function that has an input that typically is the state and has an output that typically is a control. And this is what we want to get. The one that are in equilibrium strategies, the Nash one. Why? Because the intuition behind that is if one guy is not doing the best that it is able to do, so you don't get the solution. There is something else that can be done. It's for this that you want to one guy to maximize and the other to minimize. And this is the tool. This is the tool that we are using. That is the Pontryagin maximum principle. What is this thing that is H? And H is called the Hamiltonian of the system. The Hamiltonian of the system in physics is a measure of energy. It's measuring the energy of the system plus the time or the payoff that in this case is the time. And there is something that is called the adjoint equation that basically is the partial derivative of the state with respect to the Hamiltonian. So to make summarize what is the method, is basically you get a differential equation, you solve this differential equation, you get the gradient of the value function, distinct, what is unknown. You use that to compute the actual trajectories of the players. And the Hamiltonian is a direct function of the controls of the players. One guy wants to minimize the Hamiltonian, and the other guy wants to maximize the Hamiltonian. So what I would like to be remembered of that is based on a Hamiltonian, the maximization and minimization of the Hamiltonian, what is equivalent to solve a differential equation, and with this differential equation, when you solve this differential equation, you will get the trajectories. And that's it. That's all the theory. Now, some results. The optimal controls of the players are the following ones. That is the first result. Are for the pursuer either to move in a straight line to maximal speed or to turn inside to maximal angular speed. Those are the optimal controls. If you integrate that, you get what we call the optimal motion primitives, what are basically straight lines or rotation inside. And for the evader, the optimal motion strategies are just straight lines in some given direction. And that's it. The second, that is the motion policy. The second question is, who is the winner? And the winner is defined for something that is called the barrier. And basically it's a dot product between the motion direction of the system, what is called F, a dot product with the normal of a circle that represents the possibility of capture the evader. So basically, if there is a motion direction that gets into the circle, there is the possibility to capture the other guys, what is equivalent to have a dot product that is smaller than 0. And the decision problem is solved by just this inequality. The ratio of the maximal speed of the evader over the maximal speed of the pursuer is this quantity. And this quantity, L, is the capture distance. How big is the circle? B is the distance between the center of the robot and the wheel of the robot. And S is the angle measured between the direction of the pursuer wheels and in clockwise sense. So basically, what you get is an inequality that tells you which of the players is going to win. And now, I will to show you the motion policy graphically. This is the motion policy. This is the reduced space. The pursuer is here. The wheels is pointing in this direction. Okay? This is perpendicular. And there are, let me simplify this. There is two regions. One here, if the evader is here, this guy has to move in a straight line. No, sorry. If the evader is here, the pursuer has to move in a straight line. And if the evader is here, in the blue, in the green or yellow region, the pursuer has to rotate in place to maximal speed. And you have a direct mapping between the state and the control. Let me show you an example. Good question. The difference between the yellow and the green is, in one case, you will catch the guys pointing in the, well, let me go more slowly. In one case, you will catch the other guys with the wheels pointing in the direction of the line between the center of the reduced space and the body of the evader, and in other case, you will catch the guy with some angle, not in front of them. But in both of the cases, the optimal control is the same, just to turn in place. And if the evader is here, the optimal control is just to move in a straight line. So let me show you an example. I hope that will help me to. This is the optimal motion of the two guys. Just to move in a straight line, one, this is the pursuer, that is the evader, that is the reduced space, you know, from the point of view relative to the pursuer, and this is the Euclidean plane. Let me show it again. This is the evader, moves in a straight line. This is the motion policy that is the one that maximizes the capture time, and this is the one that minimizes the capture time. And one that I think is more interesting, I hope so, is when the evader avoids capture. Is this one? And this is the most favorable initial condition for the pursuer. It's just in front of him. But the barrier is closed, and it separates the plane into regions. At this moment, the system starts sliding over the barrier. And at a point, the pursuer just touches the evader, but is not able to reduce further the distance. And you get in a cycle. And this cycle never ends. Do you get the intuition? It's one and over the same motion direction, and the distance is never reduced that this critical condition, where one guy touches the other, but is not able to get closer. Again. Look in the reduced space. The barrier is closed. So the pursuer is changing the motion direction. The evader is changing the motion direction. The pursuer touches the evader, but never gets closer. Because of the position in the reduced space. You know, there is a direct mapping. I am here, I am in this region, I have to do this. And when I change region, I change my control. I think I'm going to go faster, but I hope I pass the main ideas. One other result is that this partition of the reduced space can be represented as a graph. And the graph has this structure where you don't get this kind of problems, where being in an state is connected with other two states that has the same local cause. That is a problem because it's equivalent to a local minima. You can choose this or that, but at the end you will not know what is the best control to apply. But that does not happen in our problem. Our problem, the partition of the state space that represent this graph has this structure, and indeed, locally optimal controls are globally optimal controls. But it's a pretty nice property. I think we get lucky in that. And another important thing is that in order to get a closed loop motion policy, you need to know where is one guy with respect to the other. For estimating that, we are using something that is called the 1D trifocal tensor that basically use another local reference frame to know where is the pursuer this time with respect to the evader. And in this way, we can get an motion policy based on feedback, and that is the result. This corresponds to a simulation in a closed loop motion policy where the state of the evader relative to the pursuer is estimated using image, and estimating the position of the evader in the local reference frame of the pursuer, where it makes a direct mapping to the motion policy. So basically that's it. That is the first problem. What I had presented is what are the techniques. The techniques are the Pontryagin maximum principle, what is based on the maximization and minimization of the Hamiltonian, and gave you the optimal controls of both players, and if you integrate this control over time, you get the trajectories. For the evader, the optimal trajectories are just straight lines, and for the pursuer are straight lines or rotation in place. And the decision problem is solved by one inequality that basically relates the ratio between the maximal speed of one player and the other player and some parameters of the system, what is the capture distance and the distance between the wheels and the center of the robot. And we get a motion policy in closed form, where you get the state of the evader relative to the pursuer, and you know which are the optimal controls that have to be applied. Some questions until here? Do you have some questions? No questions? It's clear? Both the problem and the solution? I hope so. I have not too much time, but the second problem is, now imagine that you are in a environment with obstacles, and you want to maintain visibility of one guy with another guy. And in these other games, the players are homogeneous. Both are omnidirectional agents, can change motion direction instantaneously. There is no restriction on the motion, but the problems are the obstacles. So what we want to know is this thing. We want to answer a decision question. Is the evader able to maintain visibility, or is the pursuer able to maintain visibility of the evader at all times? And that's the question, in an environment with obstacles. And this is a problem that seems to be easy, but that we had not been able to solve. You know, this is the pursuer, this is the evader, this is an obstacle. The guys are, the light outside between the pursuer and the evader is touching the obstacle. It's about to escape, okay? And we know that the locally optimal motion direction for the pursuer is to move in an arc of circle centered in this point. That will reduce the shadow region as fast as possible. Okay? However, the evader has the ability to look for a second occlusion, to get and hide behind this other point of escaping. To avoid the second possibility of escaping, the pursuer has to travel in a straight line in this direction, because it's the one that minimizes the distance between this point and this line that will prevent the second occlusion. Okay? So how to combine these two locally optimal motion strategies in order to avoid the escape of the evader in both cases? We don't know how to do that. We have been working for some time on that, and no, not yet. So if you may help us, that we will be glad to have any help. So basically, what we are doing is we prevent the system to get in this configuration. Okay? We say that is too hard. That is too hard for the pursuer. Let's avoid a situation that is that hard for the pursuer. Let's prevent, let's plan ahead on time, and for doing that, we are establishing something that is a strong mutual visibility. A strong mutual visibility is we divide the environment in a partition. We had regions, not overlapping regions. And one region is said to be a strong mutually visible of the other region if every point in a region see all the points in the other region. So for instance, region A and region C are strongly mutually visible. However, region A and region G are not. There are points in region G that are not seen by all the points in region A. What is the hard situation that I presented you before? Okay? So basically, we establish, we model the problem like graphs, and this is, I think, the basically idea. You know, the evader can be hidden by an obstacle if it is behind an obstacle. The obstacles are, I mean, I cannot see through the obstacles. They impose motion and visibility constraints. So basically, every corner in the environment is a possibility for the evader to escape, okay? So when the evader is in a corner of the environment, we have to reason about all the regions that are adjacent to this corner, okay? And we have to reason in the Lociot points that is able to see all those regions at the same time. So basically, for avoiding the escape of the evader, this is a possibility. But this is a region where the pursuer has to be in order to avoid the escape of the evader through this vertex. Okay? So it's like playing baseball. You have base, and you have to reach the base before that the ball gets there. And that gives you discrete locations that are like shoot goals that you have to visit, satisfying some time constraints. And this is the whole idea. So this data structure is called the reduced visibility graph. That is basically the roadmap that encodes the shortest path between any 2 points in the environment. So for this problem, we are assuming that the evader is moving in this network. I think that is reasonable because it's the shorter distance to escape. It's the shorter distance to get to a vertex that is a possibility for escaping. And let me use that. So basically, the problem is this one. If the evader is here, the pursuer has to be in this green region, and when the evader is moving between these two vertices, the pursuer has to move between the two regions that prevent the escaping for that vertex, assuming that the evader is moving in the visibility graph, meaning in the shorter distance to escape to the other, in the shorter distance to the other vertex. And the result is this thing. There is some regions of the space, the green regions, where the pursuer must be when the evader is at each of those vertices. And these regions are such that can be reached by the pursuer in the same time or a smaller time that is needed for the evader to travel between vertices. And that is nice for reduced visibility graphs that has a structure like this one without cycles. That is enough to solve the problem for shortest distance to escape that has this structure, no cycles on it. But imagine that you get a cycle in the reduced visibility graph. A cycle in the reduced visibility graph is basically something like that. You get an obstacle in the interior, and the pursuer may turns around this obstacle forever. So basically, what we are doing is unfolding these graphs into trees, but these trees have to be plotted again, put it again in a structure like that. And every copy of the tree is a cycle over the obstacle. Okay? But the question is this process going to converge in finite time? Or I am going to be turning around an obstacle forever without knowing which is the winner? And that is what, in theoretical computer science, is called a decidability problem. You know, a very famous decidability problem is the halting problem. Is this program wrong, cycle forever, or is going to terminate? Okay? So basically, that is the question that we are trying to solve. Are we able to telling who is the winner in finite time or not? And this is some graphical representation of the solution. The green region is the places where the pursuer must be at the time when the evader is in a reflex vertex, but our modeling always allows us to have the motion strategy for the pursuer, not only at the reference vertex, but at every instant of time during the motion of the two guys. And this corresponds to be in this yellow region here. So you can see as the pursuer is, as the evader is getting faster and faster, the ratio between the two is getting slow, the ratio of the velocities is getting smaller and smaller. The places where the evader, the pursuer has to be, get smaller and smaller. there is less possibilities to avoid the escape. And that's it. The two results are theoretical. The first one is the problem is decidable. You can give an answer in finite time. Our process to putting unfolding graphs into trees is finite. And the second one is, what is the bad news? The time is empty complete. Basically, there is a special case of the problem what is exactly the same that the bottleneck traveling salesman problem. So a particular special case made the problem very complex from a computational point of view. And just the conclusion. In the first part, we get the following results. We present time-optimal motion strategies and the condition defining the winner for the game. And for surveillance with obstacles, we prove the decidability of this problem for any arbitrary polygonal environment, assuming that the evader is traveling in the reduced visibility graph, what is still a restriction. And we provide a complexity measure to the surveillance game. Future world, what I think is the most important part, is what about if one single pursuer is not able to catch the evader? How to manage to make two guys cooperate, two pursuers cooperating for catching the evader? And also, this is first order dynamics, meaning bounded velocity. We would like to address higher order dynamics. And for surveillance with obstacles, we would like to allow the evader to move in all the paths, not only in the reduced visibility graph. And well, of course, another interesting word is surveillance with drones. Where I put drones. Yes, Pursuit-Evasion with drones, which considering the dynamical constraints. That will be cool to have like networks of pursuers that are cooperating to finding or catching an evader, what is also flying or in the ground. And another possible extensions are, what about, have you seen this movie? What is the name? The War of the Wars, La Guerra de los Mundos, in which you have something, I don't know, it's a robot or it's a biological system that is looking for someone with a lot of degree of freedom. You know, it's like a snake. Well, our version of that is this thing. A mobile robot with an arm and a camera mounting on the end effector. So basically, are the same problem in higher dimension with many degrees of freedom. And that is something that we have been trained to do for like 2 years, right, Luis? Luis, what is a postdoc here, was my PhD student, and that is his video, and was his future work, what is still future work. So I think I am done. If you have questions, I will try to answer.
Thank you, Rafael. Thank you very much.